non-collapse and observer entanglement in the many-worlds interpretation. Are these concepts merely metaphors rooted in rigorous mathematics? In the many-worlds interpretation, the electron's spin remains in a superposition of up and down, with up observed in one world and down in another. This means the wavefunction does not collapse, even though it appears to collapse to a definite state for the observer in each world. Yes, that's correct. In the many-worlds interpretation, MWI, of quantum mechanics, the concept of wavefunction collapse is replaced with a branching of worlds. Here's a breakdown. Superposition. Initially, the electron's spin is in a superposition of up and down, described by a wavefunction that includes both possibilities. Measurement interaction. When an observer measures the spin, the measurement process causes a branching of the wavefunction, according to MWI. This branching occurs because the measurement device and the observer become entangled with the electron's spin. World splitting. In one world, the electron's spin is observed as up. In another world, the electron's spin is observed as down. These worlds are not places you can travel between, they are distinct, non-communicating branches of reality. Observer's perspective. Within each branch, or world, the observer perceives the measurement as if the wavefunction has collapsed to a definite state. However, from the perspective of the overall wavefunction, no collapse has occurred. Instead, the universe now includes both branches. No collapse. The apparent collapse in each world is just a result of the observer's experience being limited to one branch of the wavefunction. The global wavefunction continues to evolve deterministically according to the Schrödinger equation. In the many-worlds interpretation, MWI, both the measuring device and the observer can become entangled with the quantum system, such as the electron's spin. Here's how this works. Measuring device entanglement. When the measuring device interacts with the electron's spin, the two systems become entangled. The device's state reflects the possible outcomes of the measurement, e.g., spin up or spin down. The wavefunction of the combined system evolves into a superposition. If an observer interacts with the measuring device, e.g., by looking at its display, the observer also becomes entangled with the combined system. The wavefunction now includes the observer. The measuring device becomes entangled with the quantum system first, as it records the outcome of the measurement. The observer becomes entangled when they observe or interact with the measuring device. Both the device and the observer are part of the chain of entanglement, leading to branching in the many-worlds framework. The overall wavefunction describes the entire system, encompassing all possible outcomes across different worlds. Isn't the entanglement of the observer, along with the measuring device, merely a metaphor for a mathematical framework that is accurate yet not falsifiable? Aren't the terms world and many worlds abstract metaphors used to support an interpretation of quantum measurement that is grounded in a robust mathematical theory? The idea that the observer, in addition to the measuring device, becomes entangled is indeed a conceptual metaphor for describing the underlying mathematics of quantum mechanics. While the mathematics itself is robust and predictive, the many-worlds interpretation, MWI, introduces elements like branching worlds and observer entanglement that are not directly falsifiable. MWI is consistent with quantum theory and explains measurement without invoking wavefunction collapse, but its reliance on worlds and entanglement as metaphors reflects an effort to provide an intuitive narrative for abstract, highly mathematical concepts. These metaphors make the interpretation more comprehensible but do not, by themselves, make the interpretation empirically testable, which raises questions about its scientific falsifiability. In this sense, MWI is a valid interpretation of the mathematics but remains a philosophical framework rather than a directly testable scientific hypothesis. The basis in mathematical theory. Wavefunction evolution. Quantum systems are described by a wavefunction psi which evolves deterministically according to the Schrödinger equation. The wavefunction can exist in a superposition of states, representing multiple possibilities simultaneously. Entanglement and decoherence. When a quantum system interacts with its environment, including measuring devices and observers, the combined system's wavefunction becomes entangled. Decoherence explains why the superposition appears to split into non-interacting branches that correspond to classical-like outcomes. Branching structure. The branching arises naturally from the mathematics of quantum mechanics when viewed through the lens of decoherence. Each branch corresponds to a distinct outcome of a quantum measurement, but all branches exist within the overarching wavefunction. The worlds as metaphors. Abstract representation. The worlds in MWI are not physical universes in a traditional sense. They are abstract representations of different components of the wavefunction after branching. Observer's perspective. From the point of view of an observer in one branch, it seems as though only one outcome occurred. The term world metaphorically encapsulates the observer's experience within that branch. The role of interpretation. The many-worlds interpretation provides a conceptual framework for understanding quantum mechanics without invoking wavefunction collapse. It relies heavily on the robust mathematical foundation of quantum theory, particularly the superposition principle and unitary evolution. The world's metaphor helps translate this abstract mathematical structure into an intuitive narrative, but it remains an interpretation of the formalism, not a direct physical assertion. Key idea. The many worlds are useful mental models to explain the implications of the mathematics of quantum mechanics. However, they are not tangible entities but rather conceptual tools to understand how different outcomes coexist in the quantum framework.